Hello everyone, welcome back to CP 517-WS Digital and Computer System Architecture. This is part 2 of lecture 9. We're going to talk about GPU instruction set. So NVIDIA's GPU instruction set architecture is like this. They call it PTX, Parallel Thread Execution, PTX. PTX, yeah. Okay. So for PTX, what they do is they essentially have an opcode type, like it is signed 32 floating point 64, and then the destination has 3 sources, potential sources. Okay, they use a virtual register. So basically, the registers, number of registers are not yet determined. Well, the total number of register utilization is actually done when we translate this kind of PTX into machine code. Okay. For instance, in this code, what we do is we multiply the block ID by factor f. We shift left side by 9 digit, and then because the block size is factor f, or 229. Okay, and then we add the thread ID to the R8. It actually gets our CUDA thread ID in total, the R8. Since it's thread centric, so what we do is we use the thread ID to index the memory and load the data to register. And then we also use the thread ID plus the base memory address and then put it in the second register. What we do next is we do multiplication and then store it in that register. And then we also do addition. Okay, so this is the same as AX plus YI, because this is YI, this is X, and we assume RD4 is the A, scala A. Okay, then we store the result back to Y. I. Right? So this is the PTX code of CUDA's implementation of sexpop, right? What do we mention about here? Sexpop, dexpop. Okay. Well, for conditioning, GPU uses internal masks. Basically, GPU has a branch synchronization stack. The entries consist of masks for each GPU thread, where thread commits the results when they take or not take the branch. Instruction markers will be used to manage when a branch diverges into different execution paths. Like you have this kind of branch. If thread ID is even, we do something. Else, if they're odd, do other things. So we can see here, they're gonna have branch divergence because some threads execute this path, some thread execute this path. So we see a branch divergence into multiple execution paths. Then we call this branch divergence. Then what we do is NVIDIA will serialize the execution. So all the threads gonna be executed in lockstep. So some threads working here, other threads gonna be waiting here. Okay. And then once it goes to else, the waiting threads, which are even the odd threads, sorry, the odd threads gonna continue to execute the else, and then the even threads gonna be here waiting. So this is called the branch divergence based lockstep execution. And then when path converges, they act as like a barrier, like a lock, what I mentioned before. We pops out the stack. They use per thread 1-bit branch predictor predicate to see whether the threads should be executed or not. Can be specified the programmer. This is the thing I mentioned about. Right, so if xi not equal to 0, we do xi equals xi subtract yi, else we do xi equals zi. So here's the PTX. So first we load the data of xi, and then we set the predicate for register I, right? And then we push auto mask and set new mask bits. If P1 is false, we'll go to else 1, right? Then we load the yi, and then we perform subtraction of xi subtract yi, and then we store the result back to xi. Then we do complement the mask bits. If P1 is true, we go to end, right? Which means the next iteration, next branch, okay? So basically, you can see here, this is the branch divergence, right? We basically push the old mask, set new mask bits. If P1 is false, then we go to this branch. For this branch, what we do is we load the value of zi and then set xi equals to zi, which means we store the zi's value to xi's address. The comparison between the vectorized architecture versus GPU are that both of them SIMD processed are analogous to SIMD processor. Registers for vectorized registers codes the entire vector. GPU distributes vectors across the threads or SIMD lengths. For vectorized computer, they have 32 vectorized registers of 32 elements, while GPU has 256 registers with 32 elements, which is much more. GPU vectorized loop is grid. All GPU loads are gather instructions, and all GPU stores are scatter instructions. Well, before we move on to the tutorial of the AVX and GPU, let's first discuss a couple of loop carried parallelism slides. What is loop carried parallelism dependency? It is actually whether data accesses in later iterations are depending upon the completion of the prior ones. For instance, in this one, the data dependency is there's no data dependency across iterations because xi only depends upon xs value. However, here you can see the value of current iteration will affect next iteration's results, right? Like S2, S1 and S2 use the values computed by S1 in previous iteration, right? So that's the problem. well, S2 uses the value computed by S1 as well of the same iteration of AI plus 1. But for this BI, AI, CI, they are from prior iteration, right? Okay, so finding the data dependencies across loops. In this one, we don't have that. Oh, yeah, we do have, sorry. We do have that because you use prior iterations updates to compute S1, S2. Well, the problem is it's more complicated. Sometimes you cannot just, by, different rules to do that. Right? We have to come up with some rules. The general rule is one-dimensional array access of AI plus B, where I is the loop iterative variable. If two references AI plus B equals CI plus D, then if this exists, D subtract B must can be evenly divided by the greatest common divisor of C and A. This is based upon the linear Delphanten equation, which we have a theory here. For those people who are interested in, can take a look at this equation. Okay, so see here, this is B, this is A, this is C, D equals to 0. You can see that D subtract B equals minus 3, and then A and D, the greatest common divisor, great common divisor is, sorry, it's the greatest common divisor. It's not great. Greatest common divisor is 2. As you can see, minus 3 cannot be evenly divided by 2. So there's no loop carry dependency. As you can also analyze that by no matter how you increase this one, you can never evenly compensate this 3, right? So that's the reason that we cannot find there does not exist a loop carry dependency. Find onTie and output dependency. See here, S2 is dependent upon output dependency is right after read. Right after read, right? For right after write, this one. Right. So it's output dependency and onTie dependency. Reductions. What is reduction? Reduction actually means we combine all the values, reduce it to a single sum, max, or minimum, etc. Right? So these are reduction functions. These are very hard for us to implement on GPU or FPGA or Vectorized machine because it requires to communicate across different data. So the parallelism requires communication. That's a problem. Previously, it's xi, yi, and xi plus 1 and y plus 1. There's no dependency. But if it concerning about we combine all of this x0 to x1024 to a single value, that requires the communication between different data. As we know, it's data level parallelism. So if the parallelism involves some communications, it becomes a problem, right? Okay, so I think that's that for GPU part.